In this video, we'll be looking at a concept called colligative properties of solutions. These colligative properties will help us answer questions such as why cities put salt on the roads during the winter, and why you can't drink seawater, why that doesn't actually help hydrate you, but in fact makes you even thirstier. So to begin with, colligative properties of solutions are properties that depend on the amount of solute or the concentration of solute, but not on the identity of that solute. Concentration of the solute, not on the identity. That is to say, what matters is how much of the solute you have, not the identity of the solute. For our video, there's 4 different colligative properties that we're going to be concerned with. As I mentioned, one of them is why cities put salt on the roads during the winter. And it turns out that by dissolving salt into water, you actually drive down the freezing point of water, something called freezing point depression. Now, because of this, it takes a colder temperature for water to freeze, maybe -2, -3, -4 Celsius, which means if the temperature is hovering right around freezing, salted roads will remain liquid water and not freeze to ice, which is going to be safer driving conditions. Because this is a colligative property, what really matters is the amount of solute, not the identity. Salt is used because it's relatively cheap and splits into Na+ and Cl- ions, or if using calcium chloride, Ca+ and 2Cl- ions, generating a lot of solute. Another colligative property is boiling point elevation. That is to say, when you dissolve a solute into water, the boiling point of that water rises. Now, the reason we salt water when cooking something like pasta is more for flavoring than for boiling point elevation, but a nice little quirk of doing that is it actually does drive up the boiling point slightly and gives you a hotter temperature for that boiling water. A third colligative property that we're looking at is osmosis. Osmosis is the movement of water across a membrane. This is something we're going to study in a little bit more detail in a future video, but for right now, you can tell that depending on the concentration of blood outside of a blood cell, water might flow into or out of that red blood cell. Thinking about the question at the beginning of the video, why can't you drink salt water? Well, salt water is very, very highly concentrated. There's a lot of salt dissolved in it, and that's going to create something called osmotic pressure, which causes water to flow from inside the cell out, actually dehydrating you rather than hydrating you. Again, we'll focus on this in a future video. A fourth colligative property that depends on the concentration of solute is conductivity. The more ions you have dissolved, the better water is at conducting. Fewer ions, you have a weak electrolyte and much less electrical conductivity. Now, we're concerned about quantifying 2 of these. That is boiling point elevation and freezing point depression. And to do that, we need a concept called molality. Molality is described as moles of solute divided by kilograms of solvent. It's a way to describe concentration. And this is using a small m as the symbol. You might describe something as having 3 molal, or a solution being 3 molal, being 3 moles of solute per kilogram of solvent. Notice that it's subtly different from molarity, which is moles of solute per liters of solution. This is moles of solute per kilograms of solvent. Now, with this idea of molality, we can generate equations for both freezing point depression and boiling point elevation. Those equations are right there, where the change in temperature of the freezing point is equal to the molality of the concentration times a constant, K, for the freezing point. Likewise, the change in boiling point temperature of a solution is equal to the molality of that concentration times a different constant. I'll give you those constants for water, and then we'll do 2 practice problems to show how this works. So let's take these equations, take these constants, and calculate the freezing point and the boiling point of a 1.7 molal ethylene glycol solution. As shown above, the change in temperature of the freezing point is equal to the molality times a constant. So the change in temperature of the freezing point is equal to 1.7 molal times 1.86 degrees Celsius per kilogram of solvent divided by mole of solute. Looking at our units here, molality cancels out kilograms of moles of solute, giving us just units of degrees Celsius. And the math says there's a change in temperature of 3.16 degrees Celsius. Now we know that water typically freezes at 0 degrees Celsius, minus 3.16, because we're talking about a depression here, or a decrease, tells us that the freezing point of this solution is minus 3.16 degrees Celsius. Ethylene glycol is also known as antifreeze, so by adding antifreeze to water, you can prevent that water from freezing. For the final example problem, we want to calculate the boiling point of that same solution. Using the equation above, we have the change in temperature of the boiling point equals the molality times a different constant. And here the change in temperature of the boiling point is 1.7 molal times 0.512 degrees Celsius per kilogram of solvent over moles of solute. Just like before, molality cancels out kilograms of solvent and moles of solute, and we get units of just degrees Celsius. This works out to 0.87 degrees Celsius for a change in boiling point. Now we know that water typically boils at 100 Celsius. Adding in the change in temperature gives us a new boiling point of 100.87 degrees Celsius equals the new boiling point. So in total, what this tells us is a 1.7 molal ethylene glycol solution would have a new freezing point of minus 3.16 Celsius and a new boiling point of 100.87 degrees Celsius. Another way of looking at this is that dissolving a solute will stretch the liquid phase of that solution. Thanks for watching.